Okay, hello everyone. So today I'm doing a short little video on the Diels Alder reaction from organic chemistry. Just a little disclaimer, I am only an undergraduate student, but I have done quite well in these classes. So I thought I'd, maybe try and help some people understand it and give my best explanation as to how I look at it and how I was best able to understand it. So for this video today, we're going to discuss some basic rules and facts of the reaction. We are going to talk about the basic reaction mechanism. We are going to talk about how I approach it and what techniques I found help me. And then we're going to talk about the electron withdrawing and electron donating groups that we attach to our dienes and dienophiles in the reaction to change the reactivity, namely increase it. And we're going to talk about the regioselectivity and the stereochemistry of the reaction products. So, firstly, let's start off by acknowledging our diene and our dienophile. And apologies, I should have written something down before. I'm just going to write it down now, but ignore that because we will get there. So, our diene must be conjugated. First of all, this is our diene, this is our dienophile. Diene, two double bonds. Dienophile loves dienes, okay? That's the way you can think about it, and that's the way it is, really. It must be conjugated, right? So, what are we talking about? We're talking about the double bonds with respect to the single bond, right? What's a big example of a conjugated molecule is benzene, right? We all know benzene. One thing to know is there's a single bond separating each double bond. That is conjugation, right? A molecule, say, like this, is not conjugated. There's more than one single bond separating these double bonds, right? Conjugation allows electrons to delocalize, to move around, right? That's why when we draw a benzene ring here, the placement of these double bonds is arbitrary because the electrons aren't actually localized there. A more proper drawing of a benzene ring is like this, where we draw the circle in the middle and we represent that the electrons are fully delocalized. This is conjugation, one double bond separating each. In order for this, one single bond separating each double bond. In order for this reaction to work, our diene must be conjugated, right? That's why this is the most basic way people depict this reaction. We got double bond, single bond, double bond. Conjugation, okay? Now we got that out of the way. Let's talk about what's happening in the reaction. Well, we're forming two sigma bonds and a pi bond, right? We are breaking 3 pi bonds. I'll show that in more detail in a second. Sorry, I'm going to erase that. That's a little confusing. And we are breaking 3 pi bonds. And I will show that when we go through the reaction mechanism a little bit more, but just 1 second. And lastly, we will get to this, and I will show why this is the case. Electron withdrawing groups on a dienophile and or an electron donating group on the diene increases the reaction rate, right? And so I'll show that in a second, but the bullet points are, you put an electron withdrawing group on a dienophile. A dienophile is already electron deficient. It's electron poor. So place an electron withdrawing group on it, it's drawing even more electron density out of it, even more unstable, wants to react even more, right? Put an electron donating group on a diene, it's already got a lot of electron density, so I donate more electron density into it, now it's even more unstable and it wants to react, right? So we can easily, make that connection in our minds, well, why that works. But before we get there, let's go through this basic reaction mechanism. Keep in mind, this one here doesn't actually happen. In reality, if you put these two in a container together and you heated it, you're not going to get this reaction. In fact, the diene is going to react with itself in a cycloaddition, in a Diels Alder reaction, right? But for the purposes of showing how this reaction works, we are going to use it as an example. Apologies if you can hear my beagle. I'm not sure what's going on, but she's freaking out. Okay, let's talk about it. So, hypothetically, if this reaction were to happen, what do? What helps me? I found that numbering my carbons helped, and following the arrows, right? So I would always start with my diene. I'd go 1, 2, 3, 4, and then I would save the 5, 6 for the dienephile. And it just always helped me keep track of things, because sometimes as the substituents increase on our dienephile, it's just a good way to keep track of what's going on. And I also used arrows. Now, when I draw these arrows, when your professor draws these arrows, anyone like that, keep in mind, they're not actually trying to tell you what order the bonds break and form, because this is a concerted process, meaning it happens all at once. This is just a way to keep track of what's going on. So they'll draw it like this. We're pushing electrons. We're taking this pi bond, breaking it, and we're forming one here. Same thing happens here. Break this pi bond, we're forming a pi bond there. Break this pi bond, form a sigma bond here. So we're getting one new sigma bond, one new pi bond, and one new sigma bond, right? Just like I said, 2 sigma bonds, 1 pi bond formed, and we're breaking 3 pi bonds. 1, 2, 3, right? And so we can draw out the skeleton of what we had before, right? Label it 1, 2, 3, 4, 5, 6, right? And let me just grab another pen. And apologies, because this is a horrible drawing. Here's our new sigma bond, and new pi bond, right? Keep in mind a double bond is going to be a pi bond, and our single bonds are sigma bond. But I mean, if that is something that's confusing you, I would advise going back and watching a few general chemistry videos, because this is all orbitals, and it's not really going to be something covered in organic chemistry unless your professor is kind enough to go, all the way back and explain that to you. Okay, so I hope that basically makes sense. That's the basic reaction mechanism. And honestly, if you can get a grasp of this and how we're pushing electrons and how these new bonds form and which bonds are forming, you're going to do very well, right? This is going to at least earn you partial marks, right? So if you can remember that, then you're made, right? Okay. So what's this drawing here? This drawing, and this could be necessary for you, but it is an abstract concept. So just do your best to try and understand what I'm saying here. What I've drawn here is this in 3 dimensions, okay? This is how this reaction proceeds. The dienephile, right, approaches the diene from below or from above. And what happens, what instigates this reaction, is the pi bonds, they become in phase with each other. So the pi bonds on the dienephile become in phase with the pi bonds on the diene, and this allows the reaction to occur, right? And so we can draw the arrows like we did before. We can do pi bond breaking there, right? This is a little more abstract, right? Okay, we can do pi bond breaking there, form a pi bond there. And then we can do pi bond breaking there, form there, right? 2 new sigma bonds, 1 new pi bond, right? And so this becomes important when we're thinking about ideas like, stereoselectivity of a reaction. Is the product going to be cis? Is it going to be trans? And that will be more important, as the reactions get more complicated. But first, let's look at this example here, and let's talk about regioselectivity. So what I'm trying to explain here is that there's 2 potential products of this reaction, right? Let me just draw it out real quick. And apology, I wish I was faster at drawing this stuff out, but I'm just not. Okay. Okay. So this is just an example, right? There's 2 potential products here. And it's just an example, right? But what's going on here is we can either get a meta product or we can get a para product. Now this is a meta product here, and this is the para, and that is just, we're talking about the arrangements of the substituents with respect to each other. So meta being, you know, 2 carbons away from each other, para being opposite to each other, okay? How do we know which product is going to form here? Now this is one where we think about resonance structures is most helpful for me. So can we get a resonance structure here? Absolutely. What happens? We push this bond up here. We push this bond up here. Keep in mind, of course, it's a minor resonance structure, but it's enough such that we can write a partial positive charge here and a partial negative charge here. Okay, that's interesting. But how's that relevant to us? Well, we've got our electron donating group here, right? And once again, let me bring it back to my comment on electron-electron groups on dienophile and affect the reaction rate. We can see here that this resonance structure draws electron density out of the dienophile, right? In fact, we've got a partial positive charge on a carbon. That carbon is not happy. It wants to react, right? So you can see, you can understand why that would increase reactivity, right? We don't want to draw further electron density out of this, this dienophile. Well, we do if we want a reaction, but if we want a stable molecule, we don't. Now we're going to see, why does an electron donating group on the diene increase it? Well, here's why. We can push electron density here, and this oxygen can donate it here. Okay, wait, that's not correct. My apologies. So it would actually be this, right? That. So what happens now? Well, this is, again, very minor. Minor contributing structure, but it's enough. We can write partial positive on the oxygen and partial negative on the carbon, right? So now let's think about this reaction. Well, okay, we know that the negative and the positive are likely going to interact, so this reaction is actually going to be more favorable when this is flipped relative to that, because then our partial positive carbon can interact with this partially charged negative carbon, right? So what's our major product? The para is the major product, right? Keep in mind, the meta is not negligible. I believe it's about a 3-to-1 ratio, but I don't think you need to know that. So we're going to see the partial positive interact with the partial negative, and this is regioselectivity, right, guys? This is how we know where the bonds are going to form. We're going to have the para product be the major product, because when you can draw out these resonance structures and see, oh, this is how the electrons are going to push, that's how it's going to make sense. And it will help to draw out the resonance structures for yourself. I'm just doing this for sake of limited space. I'm trying to show electrons pushing out of that carbon, but you can see, right? We can see why the partial positive would be attracted to that high density of electrons at that carbon, right? Why it would flip, right? I don't know why I did the sound effects. Really didn't need that, did I? Okay, third example. This is about stereochemistry, stereoselectivity, right? What's going on in this reaction? Again, you've got some possible products. Well, I mean, I'm not going to actually say they're possible before I do it here for you. Give me just 1 second. Apologies, I'm such a slow writer. This is like embarrassing. Okay. Okay. So what I've got here, and I'm actually not going to say they're both possible until we go through this. On the one hand, we've got a cis molecule, right? Both of these substituents are pointing on the same side, and then we've got a trans molecule. Well, what are we going to get here? This is where it's important to look at the conformation of our dienophile. Okay? We've got a trans conformation here, right? If we think about this in 3 dimensions and we put these on here, well, we know we're going to have like this over here, and we're going to have this over here. So because they're on opposite faces, if we think about flattening this molecule out, right, like pulling it like this, they're going to point on opposite sides, right? And so when it's a trans conformation like this, what we're going to get is we're going to get this trans isomer, right? But we're going to get a racemic mixture of it. So no cis here, we're going to get trans. If we wanted it the other way, we have to have this molecule in a cis conformation. You can see it's trans here. These sigma bonds are on opposite sides of the double bond, right? Okay, so that basically explains that, right? It would have to be cis to get the other product. I can do some more complex reactions explaining stereochemistry, stereoselectivity in the Diels Alder if you guys are interested in that. But that is the extent. I thought I'd keep things fairly basic for the introductory video. I hope this was helpful. Yeah, I hope it was helpful. I'm so sorry if it was just completely nonsensical. But yeah, I hope you guys enjoyed. And yeah, I mean, leave a like. Feel free to share if it helped you. Obviously, don't share if it didn't help you. Thank you for watching.